Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where we talk about everything I want to that's science and math. And this is a chemistry video where we are going to learn about heat. So this is heat and gas laws. I'm going to make gas laws into a separate video, so this is just going to be about heat and energy. So come join us and you can learn about this too. Okay, so heat. Our first question is, which do you think has more heat? I said a teacup of boiling water or Lake Allatoona, which is a lake near here, which I just like the way it sounds. It's fun. Allatoona. It has tuna in it. It sounds like the fish, so it's just funny. Which one do you think has more heat? It turns out that it is the lake. That it doesn't matter that the teacup is boiling, that the heat is all the energy. And a great big lake has way more energy than, I'm going to turn and draw so I can write on this, than just a little teacup, even if the teacup's hotter. Okay, so which one has more heat? A teacup of boiling water or Lake Allatoona at 60 degrees? It's Lake Allatoona. Or we could have, I usually we'll say the ocean, because everybody knows what that is, but not everybody knows what Lake Allatoona is. All right, so what is heat? It is the total amount of energy that can be transferred, the total amount of energy in something. And it can be transferred from high temperature to low temperature. So this is where the confusion comes in. There is extreme close-up, doodly-doo, doodly-doo, I feel like Batman. Anyway, focus. This is where the confusion comes in, is there is a relationship between temperature and heat. Heat flows from areas of high temperature to areas of low temperature. But temperature is not heat. Temperature is the average kinetic energy, but we're not there yet. So what is the units of heat? It's not degrees Celsius, that's temperature. Heat is an energy unit, so it's in joules. And it's not spelt like diamonds and stuff. It is Joules, joules. Okay, so what is temperature? Temperature is the average kinetic. Remember, kinetic is the energy of motion as opposed to potential. It is the average kinetic energy. I'm still kind of learning how to write on this thing. I'm trying to do it a little bit neater. It's the average kinetic energy, and it's measured in science, we measure it in degrees Celsius or Kelvin. Now, in real life, here in Georgia, we measure it in Fahrenheit, degrees. Now notice that Kelvin doesn't have degrees. We don't usually use Kelvin even in science, but we are going to use it you'll learn in the next video, when we do gas laws. So gas laws does use Kelvin. All right, so now then, and then the other thing is we know that has to do with all of this is that there are different phases of matter. You can have ice, you can have water, you can have steam, and they all have something to do with energy and temperature, don't they? Yes, they do. So it takes energy, and remember the science symbol for energy is big E. It takes energy to go through phase change. How did I get writing all over that? What's up with that? I must have been scribbling on it when I didn't realize. I need to erase this. Go away, all that scribbling. Somehow I did. We'll go back to draw. I like the purple. And look, if you saw my last video, I kept having to run over to the computer and scroll. I've learned how to make the smartboard scroll. I know, it's exciting. So I'm going to do it. Let's hope it works. There it was. Look at that. Scroll, scroll, scroll. Oh, look, I still have scribbling on this thing. I'm going to do a little more erasing. All right, that looks nicer. Draw, go back to draw. Give me back my pen. All right, so phase change. So this is what I was talking about, going from solid to liquid to gas. Here is a graph. And in it, temperature is right here on this side, and the energy put is this side. So say energy input, imagine that as your stove. You put on the heat, and the energy is created by the stove, and it goes into your ice. You've got a black ice, you put ice in a pan on your stove. Okay, so at first the ice is very, very cold, way below freezing. And as you're heating it up, its temperature goes up and up and up until it reaches freezing. Once it reaches freezing, which is 0 degrees Celsius or 32 degrees Fahrenheit, then the ice will start melting. And when it does, it will stay at this temperature. And here we're going to say 0 degrees Celsius. It's going to stay at that temperature. Even though we're still heating it up, it's still on the stove. It's not going to get any warmer until every bit of the ice is melted. All the energy is going into changing the ice into water. It's called latent heat. L-A-T-E-N-T. Latent heat is when you're adding energy to something, but it doesn't heat up. And all the energy is being used to break the water molecules, or whatever it is, out of the crystal lattice, and where it's free to move around. Then, once every single bit of the ice is melted, it'll start heating up again, and it'll be a liquid. And that's called sensible heat. It's all sensible. It makes sense. You add heat, and it heats up. Sensible heat. That's latent heat. A little H there. Then it gets to the point where it's boiling, right here. And when it starts boiling, then all the energy goes to get the gas, the water molecules, or whatever it is, separated from the other water molecules and turn it into a gas. And it will continue staying at that temperature. So for water, that is at 100 degrees Celsius. So it will stay, or 212 degrees Fahrenheit. It's going to stay there until every bit of it turns to a steam, and then it'll continue heating up, and that will also be sensible heat. There. All right. So temperature doesn't change. And remember the symbol for change is a triangle. Temperature doesn't change while phase change is happening, even though you continue to heat it up. Now, we kind of already tell this. Melting and boiling happen at specific temperatures. For water, ice melts at 0 degrees Celsius, and it boils at 100 degrees Celsius. And we already said that's 32 degrees Fahrenheit. But we don't use Fahrenheit in science class, but I just tell you so you have a frame of reference. And boiling is at 212 degrees Fahrenheit. Now, there is some things that have to do with pressure and all that, but we're not talking about that right now. Now, there is another phase change. I'll scroll this up using my new skill. There is another phase change besides melting and boiling, or freezing or condensing if you're going the other way. It's called subliming. It sounds like heavenly. It is sublime. And sublime is when it goes directly from a solid to a gas. When it goes directly from a solid to a gas. And the temperature of subliming depends. Let's see what I wrote. It depends. It depends on things like the dryness of the air and the pressure. But it can happen. I remember when I was a kid going to public school, we would have snow days. And if it snowed and there was snow on the ground, then the buses couldn't drive and we got the day off. And it was, woo, party time, because it was a snow day. Well, one time it snowed big. We had 6 inches of snow. Everything was covered. Nobody could drive through at all. And I knew that we were going to have a snow day, that we were going to be off. And I looked at the weather, and it was going to stay below freezing. There was no way that was going to melt. I was counting my snow day, so happy that I was not going to have to go to school. Woke up, and the snow had sublimed. I was so mad. It had gone straight. It was very, very cold. It was below freezing, but it had gone straight from the snow, the solid, to a gas. And it was because the air was extremely dry. And so even though it was below, so it went straight from solid to gas without ever melting. So disappointing. Just no good to have snow and not get out of school. Now, I'm not supposed to say that because I'm a teacher. Oh, I see, it's my coat that's writing on this thing, I think. I'm supposed to be like, hey, you love school. You always want to come. But, I know about those snow days and how precious they are. And it's dastardly if it sublimes. All right, we talked about that. Okay, so the next thing is there is a property of substances called specific heat. And it is a property of the substance. You look it up in tables. So like you can look up the specific heat of gold. You can look it up for water. You can look it up for stainless steel. And it's a property of the substance. And you already probably have experienced it some, okay? So this is the heart of the matter. Which cools off first? Imagine you have a big pot full of boiling water on the stove and you turn it off. And you have another pot that you turned on and you didn't realize that you had turned the eye on underneath it and it was real hot. And you turn them off at the same time. The boiling water, which you meant to, and then the empty aluminum pot that had got hot because it was empty and you turned it off. And they started off the same temperature. But then in a few minutes you come back, which one has cooled off? Has the pot of boiling water cooled down to room temperature or has the aluminum? It's the aluminum. Aluminum heats up quickly, but it also cools off quickly. Water heats up very, very slowly, but then it holds that heat for a very, very long time. This is because they have different specific heats. They have different properties. And water has a high specific heat. And aluminum has a low specific heat. So things with high specific heats take a long time to heat up, but then once they heat up, they take a long time to cool down. Things with low specific heats can heat up quickly, but then they cool down quickly. It's just a property of the substance that has to do with, of course, the atoms. Everything has to do with the atoms, doesn't it? Now, so in particular, why does water have a high specific heat? Well, I've told you before that water is shaped like Mickey Mouse. M-I-C-K-E-Y-M-O-U-S-E. Mickey Mouse. Donald Duck. Okay, Mickey Mouse. Now, I say it's Mickey Mouse, but it's oxygen is on one side, and then hydrogen's on the other. So see, that looks like Mickey Mouse. And the oxygen is negative, so I say it's unimpressed Mickey Mouse, and the hydrogens are positive. And then my students say, no, Miss Blackburn, it looks like Kermit the Frog. So unimpressed Mickey Mouse or Kermit the Frog, either way, it has a positive end and a negative end. It's because oxygen's a bully and is a hog with the electrons. And so it ends up being more negative, and the hydrogens, who hardly ever get to see the electrons, they're kind of positive because they never get to see their electrons. So it looks like Mickey Mouse, and it's polar. It has positive ends and negative ends, just like our Earth has ice ends, and that makes water stick to itself. So it sticks to itself, and that makes it. I had to make sure. I heard bang, bang, bang to make sure. There's another teacher who she might get locked out, and I might need to go let her in. But she's going to text me, and she hasn't texted me. So that bang, bang, bang is the band playing the drums. Anyway, so water sticks to itself, and that stickiness causes it to be slow to heat up and slow to cool off. It gives it its high specific heat. It also makes it where we have life on this planet. If water did not have this high specific heat, then like other planets, during the day it gets so hot it can't support life, and at night it gets so cold it can't support life. But we're covered in water, and water has a high specific heat. So during the day, our water keeps our planet cool, and it's heating and heating and heating as the sun shines on it. But then at night, it keeps it warm because it's holding all that heat, very slowly releasing it to the environment, and that keeps our planet just a wonderful temperature for us to live on all over. We can live up in Canada, or we can live down in Colombia, and either way, it's a good temperature to support life, and it all has to do with this shape of water. If it wasn't for water having its shape and carbon having its shape, we would not have life on this planet. So it's really a miracle that we have life, because it's amazing, because most planets are not covered with water. We're a very watery planet, and that's the thing. It's our wonderful water, our wonderful Kermit the Frog looking molecule up there. All right, so remember I told you this is about heat. So there is a change in heat formula. It's change in heat, and I'm going to write that delta H. Sometimes there's a different symbol for it, but different textbooks have different ones. I like the delta H because you can remember H for heat. So I'm going to use that, but later in college you might have a different symbol. Go with it. All right, so triangle H, the change in heat, is equal to, I say it's cat. See how it looks like cat? MC delta T. It looks like it's saying cat. What's the formula for heat? Cat. And that is, M stands for mass, and mass is in grams. C, we already know, is the specific heat. You look it up in tables. Specific heat. I'm writing too. If I don't write slow, it really smears it. And for water, you probably should memorize it, because a lot of times your problems are going to be for water. The specific heat for water is 4.180 joules per grams degrees Celsius, or it's 1 calorie. So there's different units for specific heat. You use the one that you need, and or that's given to you, plug it in the formula. Okay, so T is the change in temperature, and it's in Celsius. So it's delta T, actually, is change in temperature. Change in, oopsie, I wrote too fast. Change in temperature in degrees Celsius. So here's an example problem. So when you have a problem, identify your knowns and unknowns, because what makes a word problem hard? The words. So what do we want to get rid of? The words. We want it to be nice, just math, because math is easy and fun. Math is great. That's what we always say. Math is great. I'll put my problem up there. All right. So you drink 1,000 grams of water. So I'm going to label that M, because that's a mass. At 0 degrees Celsius, that's my first temperature. I'm going to label it T sub 1, or initial temperature. In U, it warms up to 37 degrees. That's my second temperature. What is the change of heat? Well, my mass, so I write my formula next, and then I substitute. You have to sing the song. And I know it's before my time too, but you just have to. You have to sing. It's by The Who. It's an old band. All right. So the mass is 1,000. We substitute that in. We write it right underneath. The specific heat that we're going to use for this one, for water, it's water. So we're going to use 4.180. And the change in temperature, it went from 0 to 37 degrees. So the change in temperature was 37. No, you subtract them, but 37 minus 0 is 37. And then you multiply them together on your calculator. So be sure to use your calculator for this. If you get it wrong, I want it to be because you didn't know your chemistry, and not because you made a dumb math mistake. Okay, so the answer is 154,600 joules, 154,600 joules. Now, how do we measure this? How do we measure this change in heat? There's a device called a calorimeter. Calorimeter, that's fun to say, like Francisco. C-A-L-O-R-I-M-E-T-E-R, a calorimeter. It's a calorimeter is how you say it. And this is a nice one. It has a thermometer. It's an insulated chamber. You can see the temperature change. You can measure that. and the heat lost by what you put in here is gained by the water, and you weigh what you put in there so you get the mass, and then you can figure it out. Now, in a high school science class, we don't usually have that. In fact, in all my years of teaching, we've never had one of those. What we use in high school science class is a styrofoam cup. And the thing is it works pretty good. You just get a styrofoam cup, you measure your water, you see how many grams you have of water, you put it in there, you heat up whatever you want to see the change in heat. You throw it in there. You measure the temperature of the water before and after you throw it in there, and you can do the problem. And we know the specific heat of water, so you always put water in them because that's just the easy one to use. So very fancy high-tech equipment. I remember the very first time I was in high school, and they said, we're going to use a calorimeter today. I was like, ooh, fancy science equipment. This is going to be great. And then it was a styrofoam cup, and I was like, really? Huh. Little disappointed, but that's what it is. All right. Moving on up. Okay, so another concept that has to do with this is the concept of entropy. Entropy is the measure of the degree of disorder of a system. So we know that a solid in its crystal lattice has more order than a gas where the molecules are just zipping around wherever they want. So entropy would be a measure of that, the amount of disorder in a system. And it's a law. There's just like there's the law of gravity, it's a law of entropy. That means it wins. If there's two scientific ideas in contrast and one of them doesn't obey entropy, entropy wins. The other idea needs more work because entropy is true like gravity. It's these laws that cannot be broken. There used to be an ad a long time ago, I think it was for Lexus, and they said, if we break the laws of science, will we be in trouble? And I would scream at the TV because I'm crazy, you can't break the laws of science! So like you can't buy a Lexus because they don't know that, so they must be like bad in science or something. It was just the ad people. The ad people aren't really the people who make the car, but still. Anyway, it still makes me like, Okay, so it's a law, and this is the law. This is what the law says, is that things always go from more order to less order unless acted upon by an outside force. So let me say, imagine that there are Legos all over your little brother's floor or little sister's, and it looks like there's been an explosion in the Lego factory. And then you come back later, and these Legos are all nice and orderly and have been made into a castle or to some Star Wars thing, the Dagobah system or something. You know that those Legos did not move themselves from disorder to order. You know that they didn't just decide, we're going to all get together and make a beautiful castle. You know that there was an outside force that put them together. Things don't put themselves together. Things don't become more orderly on their own. They become less orderly. Now, here's a chemistry example. Imagine that I take a sugar cube and I put it in some water. Is it going to stay all sugar cubed? No. It's going to go to disorder. It's going to dissolve. Those sugar particles are going to get out of their crystal lattice. They're going to go get disorderly and head wherever they want to in the beaker, and it's going to be chaos in there. So that's the same thing. Another one is that I always think about is Six Flags. I love Six Flags. I always have. And when I was a kid, there was a ride, still is, called the Dahlonega Mine Train. And they had it all decorated when I was a kid and Imagineered, where it was like Dahlonega, Georgia at the time of the gold rush. We had a gold rush in the 1830s or so. And here in Georgia, it was before the one in California, before Miner 49er. It was Miner in the 30s here in Georgia. And so they had covered wagons and they had things because this was supposed to be a runaway mine train in Dahlonega. And so out there was a covered wagon. But over the years, Six Flags just let it sit there. And at first the cover got gone, and then the wheels rotted off, and then all the wood rotted off of it, and then just the metal was sitting there, and now I think it's just like rusted to nothing. But over the course of my life, and we won't talk about how long that is, I saw that covered wagon go from order to disorder because it was not acted upon by an outside force. Now, if it had been at Disney, they would have had a force act on it, and it would have been all pretty and or put in a museum or something. But Six Flags, not so much. So it would be like, okay, you know that if there was an explosion at a metal place, Rolex watches would not come flying out of them. Nope, it would go from order, a nice little factory, to disorder, a big kaboom. It would not go from factory to explosion to Rolex watches coming out, or any kind of watches, or any kind of mechanical thing. Something can't go from disorder to order unless acted upon by an outside force. Just makes sense, right? Common sense. So don't forget that one, it's important. Okay. So enthalpy and entropy, these two ideas we just talked about, heat and this idea of the degree of order or disorder, drive reactions, chemical reactions. And that's why we're talking about it in chemistry class. It doesn't matter if these things that are happening happen all at once or if they do it in steps. The energy changes will be the same. The total energy change, whether you do these reactions all at once or in steps, and that is called Hess's law. Hess's law. He figured it out. Didn't matter. The total numbers are going to be the same whether you do it. And it kind of makes sense. Say you were going to rake your yard. You could rake a little bit and then take a break, or you could rake it all at once. Either way, it pretty much is going to take the same amount of energy to rake your yard. Hess's law. All right, so that's it. I'm going to make another video for the second half on gases. So science is great, math is great. Like, share, subscribe if you want to or not. And come back and we can learn more about chemistry.